Okay. All right. Good evening, all. We'll start. So, can you confirm whether I'm audible? I mean, whether the audio is clear enough and about the video clarity? Yes. Okay. Thanks. All right. Okay. Okay, then we'll start. Right. So, there were 2 or 3 students who informed me saying that tomorrow I know JIT exam is there, but who cares? I mean, now JIT is a very small exam, no? Right? Since it is a small exam, so I don't think it's going to be like as competitive as another exam. I mean, if you have done something enough, right, you will uh, get enough time to get ready for the exam, I guess, right? So I know we have the JIT exam, not we. You have the JIT exam tomorrow. I know. One second. All right. We'll start. Right. So YouTube is also fine, right? Okay, it's fine. Right. So we'll start. Okay then. Right. Right. For online students, I mean, for registered online students, I think you have already got the tute, right? But for today, tute won't be needed, right? But when I'm sending the other tutes, I send it along with the same package, right? And for physical students, you will get the tute in the next physical class, right? Okay then. Right, let's start. So first, the reason to start the reverse class is, right? Reasons to start the reverse class is, one is to cover things faster, right? To cover things faster. And the next most important thing is, in our syllabus, I mean, in our physics syllabus, there are some lessons which are like comparatively easier, right? But they are at the back end, at the latter part of the syllabus, right? So therefore, when we do in the like regular class, right? When we cover it in the regular sequence, regular pattern, what's happening is now even though they are small and easier lessons, since we are going to cover, or maybe in your school or some other classes, if it is going to cover like 2-3 months just before the exam, you don't get that kind of a significant, considerable time to practice those questions, right? But yet there are questions, there are units where essay questions are also coming. Definite essays are there. Questions like properties of matter, there's a definite essay. So that's what we are going to start today. And matter and radiation, there's a definite essay, right? And electricity, electronics. So mainly, and magnetic fields, mainly those are the lessons we have in our back end. And even though sometimes the theories are covered, the students don't feel that comfortable to try the question, to take the question, because they haven't practiced the question much, right? Because sometimes in the last month, properties and matter and radiation is covered in the last month, but for sure that's a definite essay question. So therefore, since you are not much familiar with the lesson, you have kind of a like fear of taking the question, right? So that's a main point. That's a main point and the main purpose behind starting the reverse class. Because now from the back end, mainly I'll be covering all the impactful lessons here, right? Then now once properties of matter is covered, for properties of matter now today we are starting now. Once it is covered, now you will have like around 7 months of time to practice questions, right? So likewise, properties of matter is going to be a definite essay question. I'll explain what the gravity of the marks here in our paper in terms of properties of matter, right? So that's the purpose. That's why I thought of starting the reverse class this time. So last time I didn't do any reverse class, right? So this time that's the main purpose behind starting the reverse class, right? Okay. And yeah, there were some students from 27 also. I think 2 or 3 students from 27 batch also registered, right? I mean, up to today, there were three registrations from 27 for 27 batch students also. So what I have to say is, if you have a requirement to cover the things faster, or if you need to sit for the exam 1 year before, something like that, because there are students who have that enough capacity, enough potential, that you can sit for the exam before. I mean, even though you are supposed to sit for the exam in 27 August, if you feel like you have that capacity and you have that potential with you, that capability with you, right, you can cover things faster, and if needed, you can sit for the exam in 26. Right? For such students also, they can take the advantage from this, right? That's also one thing. That's also one thing. And mainly, the main purpose behind starting this was to make it easier and make it comfortable and easier for 26 batch when we cover these easier lessons here. I mean, with kind of enough time, right? Enough time, considerable time before the exam, right? And for 27 paper class also, once these lessons are covered in the reverse class, we will be including questions from the lessons we are covering in the reverse class, right? So therefore, you can practice those questions for 6 months, maybe 5 months, so like kind of a time period, a considerable time period, and you can make yourself comfortable and make yourself familiar with such questions, right? So that was the main purpose behind starting the reverse class this time. Okay then, so let's get into our thing. First, let me explain. Everything is working fine, right? Okay. First, let me explain the gravity of the lesson. Gravity of the lesson, right? So all of you know that in our physics syllabus we have a segregation of lessons as 10% lessons and 20% lessons, right? So you know this. Mechanics is a 20% lesson. I mean, out of 100, out of final 100, mechanics is a 20% lesson. Oscillations and waves is a 20% lesson. Then thermal is a 20% lesson. Electricity is 20%. So likewise, there are 20% and 10% lessons, right? So when it comes to properties of matter, it is like this. When it comes to properties of matter, for properties of matter, it is like this. From properties of matter consist of 3 subunits, 3 subunits, right? Surface tension, viscosity, and elasticity. So today we will be starting off with the first subunit, surface tension, right? Surface tension. When questions are coming, this is how it's coming. For MCQs, from each there is a definite one MCQ, which means from surface tension you have one MCQ out of 50. From viscosity you have one MCQ out of 50, right? And from elasticity also same. It's also same, right? Sometimes like 2 MCQs are also coming from the same unit. So therefore, it's like 3 to 4, right? Number of MCQs is 3 to 4. And when it comes to structured essays, there's no definite structured essay. Listen, there's no definite structured essay. But when the structured essays are coming, there are practicals from properties of matter. There are, but there's no definite essay, definite structured essay, right? When the structured essays are coming, it will be replacing the mechanics essay, structured essay. Got it? So usually number 1 structured essay is the mechanics essay, no? So when a structured essay is coming from properties of matter, mechanics will be replaced, right? So it is not a definite scenario, definite occurrence. It's like it's coming like for once in 5 years, once in 6 years, something like that. Kind of a rare occurrence, right? And when a question is coming from properties of matter, it is replacing mechanics question, mechanics structured essay question, right? So therefore, for the definite marks, I'm not going to consider the structured essay mark, right? I'm not going to consider the structured essay mark for the definite marks. And for essays, essay number 7 is the dedicated essay for properties of matter, right? Dedicated essay number 7, right? According to standard structure, according to your full syllabus paper structure. Question number 7. Question number 7. And one essay, right? One essay. Here, let me write the marks. 3 to 4 MCQs means this is 3 marks here. No? Let's say 3. Abhi 3 consider karo. Let's consider 3. Then from here, this is 3 final marks. And one essay means 30 marks. 30 marks. When it comes to final marks, it will be divided by 4, 7.5 marks. Right? So as a total, this is 10.5 no? So we call this a 10% lesson in our syllabus. We call this a 10% lesson in our syllabus. Right? 10%. 10%. Definitely you can write this essay. For sure the essay is coming. Right? 7.5 marks and plus these MCQs are coming. If the structured essay is also coming, there are another 7.5, another 5 marks will be added. Right? 20 mark calculator, another 5 marks will be added to this sum if the structured essay is also, if it came. Right? Otherwise, there is not a definite essay. These are the definite marks. 10% is definitely there. Right? Out of 100, 10% is definitely there. Right? So therefore, impactful lesson. Na? So even though this is a small, actually this is a small lesson, right? Comparatively small lesson, comparatively small and an easy lesson, right? Easy lesson, but yet the impact is high. 10% again, it's a good impact. Na? 10% again, good impact. All right. So if anyone needs, you can jot it down before I jump into the lesson. No, there are no tudes for today. I saw someone has asked about the tude. There are no tudes for today, right? For already enrolled ones, I sent the tude, but even though you got the tude, today basically my plan is to cover the theory parts, right? Then by next day, we're going to start practicing the question types. Now today with the theories also, we'll discuss few example questions to you to understand the things, right? But there won't be any requirement of the tude today, right? Questions on the tude today. All right, so let's move on. Let's move on. Okay, take down the heading as properties of matter. Take down the heading as properties of matter. Properties of matter. This is also called mechanical properties of matter, right? Both are same. Properties of matter or mechanical properties of matter, right? So we know we have 3 main sub lessons, sub units under this. So first mention these 3. First one, surface tension. First one, surface tension. Second, viscosity. And then elasticity. Elasticity. Right. Mention all 3. And as heading number 1, take down again surface tension. As heading number 1, take down again surface tension. Surface tension. So basically, this class will cover like most of the theories here we have in surface tension. Right? I will try my best to cover all the theories. Right? But let's see. Let's see. Like for sure we can cover more than 85% of theories today, right? Even if we run out of time, but I will try my best to cover all the theories. Then by the next day, we can try all the types of questions at once and finish off the lesson just in 2 days. So likewise, we will move on. Right. Then under first subheading, take down surface tension. Surface tension. Right. Listen. 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 Okay. So first, I'm going to start off with a question. students who do chemistry, tell me what's the name we call for the forces between molecules, in between molecules, forces, types of forces in between molecules. In a liquid or a gas, what we call it in chemistry? So you have to respond. So I can see both chat boxes on YouTube and Zoom. Feel free to put your answers. Intermolecular forces. Good. Right? Intermolecular forces. Yeah, correct. Intermolecular forces. Now, here also, for surface tension also, the main types of forces, right? Main type of forces that is affecting is intermolecular forces. And from that also, intermolecular attractions, right? Intermolecular attractions. So we will see how the intermolecular forces are going to form surface tension, going to create the phenomenon surface tension in the next part. As a first point, write down. First point, write down. Surface tension is mainly due to. Surface tension is mainly due to. Yadurshini, yes, correct. Surface tension is mainly due to intermolecular attraction forces. Intermolecular attraction forces. Intermolecular attraction forces. Intermolecular attraction forces. So you better underline this. Intermolecular attractions. Intermolecular attraction forces. Intermolecular attraction forces. Right? Okay, again, second question. What are the two types of intermolecular attraction forces you have heard? I'm sure you have heard this in chemistry, right? What are the two main types of intermolecular attractions you have come across in chemistry? One more second. Yeah, tell me. Hydrogen bonds, no. I mean, before that, what is the basic categorization, basic classification? Hydrogen bonds are like, that's not the main categorization, no. That is under something. So what's the basic categorization? I think you have heard, and I'm sure you have heard, and sometimes in O levels also, sometimes you might have heard this. No one? No. Let me make it easy. One starts with C, the other type starts with A. So I'm sure you know this. No? Okay, then let me write. No, right? One last chance. I'm not asking about chemical bonds. Chemical bonds types kiyanne ba. I'm not asking about the chemical bonds. Right? Types of intermolecular attraction forces. There are two types. Let me make it a little bit easier. One type is between same types of molecules, and the other type is between two opposite types of molecules. Two opposite molecules. Now, what do you say now? Oh, finally, yes, that is correct. Cohesion and adhesion, cohesive forces and adhesive forces, right? So that's the two main types of intermolecular attraction forces. Who was that? Tanuji. Okay, good. See, one is called, look at the board, don't write, cohesive force. Cohesive force. Cohesive force is between same types or different types. Cohesive means same types. Same types of molecules, right? And the other one, adhesive. Adhesive force. Adhesive force is between different types of molecules. Different types of molecules, right? So those two are the two main types of intermolecular attractions we have, right? Okay, as the next point, write down. Next point, write down. There are there are two main types of mostly cohesive and adhesive, correct? Good. There are two main types of intermolecular attractions. There are two main types of intermolecular attractions. Right? There are two main types of intermolecular attractions. So since this is the first day of class, I'm reminding you this. If I forgot to turn on the recording on Zoom, right? And from your end, you will clearly see whether the recording is on or not on, right? So please, kindly remind me to turn on the recording, right? If in such a case, now today it's on. If I forgot, okay, write down first one, cohesive force. First one, cohesive force. Cohesive force. Within brackets, write down between same type of molecules. Between same type of molecules. Between same type of molecules. Right? As an example, right? So below that you can mention the examples, right? Below, or if you have some space here. Example is like water and water. Water and water. Between water and water molecules. Right? Cohesive forces. Right? Second one, adhesive force. For this lesson, only basic mechanics will be needed, right? So therefore, this is something you can start from scratch. Right? Doesn't matter whether you are 26 or 27 or 28, 29, right? If you know basic mechanics, right? The only thing you should know prior to this is basic mechanics, right? Right? Second one, adhesive force within brackets between different type of molecules. Second one, between different type of molecules. One second. Between different type of molecules. Okay. Examples between different types of molecules. Examples like water and glass. Glass in the sense, if water is in a glass container, water and glass in contact. Water and glass. Right. Look at here. Here. Say this is a glass surface. Look at the board now. This is a glass surface. And on this glass surface, On this glass surface, I have put a water droplet. Then this is how the water droplet will be here on the glass surface. This is how the water droplet will be here on the glass surface. Right? Then we know, look at here, we know between water and water molecules here, between water and this water. This is water. Between water and water molecules here, right? Between water and water molecules here, we have cohesive force. Right? Between water and glass molecules here, at this contacting surface, right? We have adhesive force. Right? So that's how these forces are acting on in such kind of a scenario. Got it? Take down. This is a very interesting lesson, and due to surface tension, now in the coming part next, like in next 30 minutes, you are going to see what are the phenomena which occurs due to surface tension, right? So there are like very unique and nice phenomena due to surface tension, and sometimes they are very simple things, but we have never thought of such a thing due to surface tension, right? So this is a nice lesson, right? A nice lesson we have in our syllabus, right? A nice and a beautiful lesson, right? Take it down. So how are you all doing with JIT 26 batch? How are you all doing with JIT? It's an easy one, no? And since it came to my mind, so there are some students who are not writing the JIT exam, right? So I have seen and I have heard, and sometimes students are asking whether you need to sit for the exam or is it compulsory or is there any point of writing the exam? Likewise, right? The thing is this. Now, if you are planning to pursue a career in ICT or IT, ICT in the sense ICT, IT related fields, right? There won't be such kind of a, there's no that impact with your JIT result, because if you have another paper qualification in terms of IT. Now, as an example, I'm not saying whether you are doing ICT instead of chemistry. That's not the thing, right? Say you have an IT degree as BSc, then once you got the IT degree as a BSc, then no one is going to ask you a ICT result or ICT result in your A-level exam or JIT result, right? But for others who don't have any thoughts of pursuing a career in ICT or IT related fields, this will be only one, maybe the last one and only qualification that you are going to get regarding IT, right? So therefore, in such cases, it has a validity. You are getting a certificate as well, right? So as the A-level certificate, you are getting a certificate for JIT exam, right? For JIT exam, you have a certificate, right? As the O-level certificate, it's like a paper kind of a thing. O-level and A-levels, the same kind of a certificate will be offered for JIT exam as well, right? So knowing about those general ID, JIT in the sense general ID, right? General ID is never going to be a waste, because now the total world, whole world is relying on IT, right? So you are joining the class also because of IT. Otherwise, we are not here. I might have to do this physically. And now there are students from Goal, Gampula, then you won't join the class if there was no ICT or no IT. So therefore, knowing general ID is mandatory these days, right? So unlike the era which was before like 2010, unlike that, now everything relies on IT and ICT, right? So therefore, knowing general ID is going to be like come in handy when you are moving ahead in your life, right? It is always coming handy. Right? Now, if you don't know how to install or uninstall a program from your computer, what's the point of using a computer? Something like that. General things, general things. If you don't know how to send an email keeping someone in the carbon copy or blind carbon copy, what's the point? Those are the things general idea again. You will be using it day to day, right? Now we are not dealing with mails anymore. No? Mails in the sense the snail mail post. We are not dealing with mails. Letters now officially the official mode of telecommunication now is using email. Then if we don't know how to write an email, sending to someone else by keeping another one in the carbon copy and another one in a blind carbon copy, right? Those are the things you should know, because now when you are in the university also, sometimes you will get instances to send emails to department heads, lecturers, right? Likewise, there are things. So that's why knowing it is like important. So my advice is all of you to sit for the exam, right? Sit for the exam, because that is never going to be a waste. That is never going to be a waste. Right? Basic ID, general ID. General ID. Okay, that's it. Finish now. As a next heading, write down. As a next heading, write down. Next heading. Explaining, write down. Explaining surface tension. Explaining surface tension using intermolecular attraction forces. 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 Right. Stop all your work and look at the board. Stop all your work and look at the board. And when I ask a question, you can give the answer for that particular question. Now look at the board. So this is a beaker. This is a beaker. Beaker. This is a beaker. And I have filled this beaker, say with a liquid, with water, with water up to this level. Right? Up to this level. Now, here I'm going to consider a particle like, which is completely inside the liquid like this. Some particle like this, which is completely inside the liquid. Completely inside the liquid. Now, listen. All around this single particle, in, three-dimensional, in 3D space, three-dimensional space, there are exact same particles, same water particles all around. Then between each and every water particle, between water and water, there are cohesive forces. Right? Now I'm going to mark these cohesive forces. There are plenty. So out of that plenty of forces, I'll be marking few cohesive forces like this. Right. So let's label this particle as, don't write, just look at the board, as a, okay, tell me, what is going to be the resultant force of all these cohesive forces? What is going to be the resultant of all these cohesive forces? What I'm basically asking is whether it's zero or non-zero. If it is non-zero, you have to say the direction. It's zero, very easy. It's zero. And again, look at the board. I'm going to consider another water particle which is exactly at the surface. Right? Somewhere here. Now, when the particle is at the surface, water particles are only in the below half, no? Because above, that is just air, no water particles. That is air medium. Here we have water particles. Then, so in these kind of directions, right, it will exert forces. So let's label this particle as particle B. Right. Now, what can you say about the resultant on particle B, on molecule B? Particle means molecule, on molecule B. Zero, non-zero, it is non-zero. If that is non-zero, what is the direction? Direction vertically downwards, right? So we can see correct answer, downwards, yeah, vertically downwards. So therefore, this is going to remain with the resultant of, let me mark the resultant also here, with the resultant of vertically downwards, right? So something like this, a vertically downward resultant. This is going to remain with the vertically downward resultant, right? Look at the board, don't write. So therefore, what is happening to this beaker is this. See, what is happening with this beaker is this. Now, initially, this level was, water surface was like this. Now, at each and every, on each and every molecule which is on the surface, there is a non-zero downward resultant force acting, right? So there may be plenty of, right, millions of particles on the surface, right? Millions of particles are on the surface, and on each and every particle, there is this downward resultant acting. And on each and every particle which is completely inside the surface, no resultant force acts. No resultant force, right? But on all particles which are at the surface, there is a resultant force acting downwards, right? So because of that, we know if there is a force which is acting downwards, now particles are going to move towards or tend towards that direction, no, that particular direction, no. So therefore, because of the impact of this force, this surface is getting bent like this, because of the impact of all the resultant forces acting on the particles, right? And then listen, then about these two, now I have keep these two at the same place. I mean the endpoints. So about the endpoints, the reason is this. Listen, about the endpoints in the sense the points which are in contact, molecules which are in contact with the glass. The thing is, adhesive force between glass and water for water is greater than cohesive force between water and water. So therefore, this adhesive force is greater. Since that adhesive force of water is greater, right? So I'm using water for the explanation, right? Just for the explanation. Otherwise, don't get a misunderstanding that each and every liquid is going to behave the same. No, right? It depends with the liquid. Now, if we use water for the example, for the explanation, cohesive force is less than the adhesive force between glass and water. So therefore, the endpoints are held by the adhesive force, right? Okay, now this is the thing. Tell me, from these two surfaces, now initially the surface was like this. Look at the board. Initially the surface was like this. Now the surface is bent like this. Surface is bent. It is curved, right? It is curved like this. Tell me, in which one the length of the surface is higher? First scenario, second scenario. Let me refer this as first and second. In which case the length of the surface is higher? Straight or curve? Which one is higher? Which length is higher? Second one, no. Simple idea. මේ length එකට මේ length එක වැඩිනේ. Right? මේ length එකට මේ length එක වැඩිනේ. හරිනේ? This length is shorter than this one, no. So therefore, this is the higher length. Now, then if we look deep down, now what has happened is, initially the water surface was like this, straight, and now it is curved. Because of the curvature, length has increased. Length is increasing means the molecules are like expanding, no? Molecules are like expanding. Since they are expanding, right? Since they are stretching, right? Expanding, stretching, that's the idea, no? The surface has stretched compared to this. Surface has stretched. Because of stretching, we know the specific type of force that is exerted on a stretching material is called, right? Tensions. Stretching on tensions, compressions on thrust forces. Now these are stretch, no? Because of this stretch, the surface is get a tension now. It has got a tension now. Therefore, this phenomenon is called surface tension, right? Therefore, this phenomenon is called surface tension, right? Okay. Any questions? Any questions? So this is how the resultant force is going to act. You can ask if any questions, and raise your hand if everything is clear up to this point. Raise your hand if everything is clear up to this point. In YouTube, I don't think we have a raise hand option. So what you can do is put to the chat, a thumbs up or raise hand or anything. Here, how many? 6, only 6. What about others? Okay, right. All right, then take this down, and you should be able to listen. The learning outcome here is this question will be asked from you. Then you should be able to explain this, what we are doing here by your own. You should be able to explain this, right? This has been asked several times. You are getting questions in essay papers like explain the occurrence or phenomenon of surface tension using intermolecular attraction forces. Then this is what you should do, right? Take it down first. So therefore, in surface tension, we don't have straight liquids. I mean liquid surfaces. In surface tension, we don't have straight liquid surfaces, right? You will see curved surfaces. You will see curved surfaces. Curved liquid surfaces are called liquid meniscus. Curved liquid surfaces are called liquid meniscus. Right? I know you have heard this word, liquid meniscus. Right? So here on, we will be referring these curved surfaces as liquid meniscus. And plural of meniscus is menisci. Right? Meniscus and menisci. Right. Take it down. Make on that. This is just for your explanation. Only these two diagrams. And now the storm is, I think it has gone out of the country. So in yesterday and the previous day also, I was saying, I was sharing this with the students in the class now, so you know, I guess, right? And is there anyone affected by it? I mean, in this class today, anyone affected by the what they call the low pressure zone came in? Is there anyone? Because it went from like entered the country somewhere in Batty, I mean in between Batty and Tringo, and then it went through like Mulativ area, Kilinochi, Mankulam, that area, and from Mana side it went out. Now it's completely gone. Now it's completely gone. It has completely gone. So I checked in the evening in the sense around like 4:30, right? So it was leaving the country from the Mana side. Now it has completely left. It has completely left. So no one is here who got affected, right? I mean, hopefully. Right. Okay, write down below. Write down below. First point. Now take this note down in point form. In point form. First point. First point. First point. Net resultant force. Net resultant force. Net resultant force. Net resultant force is 0. Net resultant force is 0. Net resultant force is 0 on any particle. Net resultant force is 0 on any particle. Net resultant force is 0 on any particle which is inside the liquid. Which is inside the liquid. 0 on any particle which is inside the liquid. Which is inside the liquid. Right, within brackets, write down A, capital A, within brackets, capital A, within brackets, capital A, within brackets, capital A. Right? Second point, but there is a downward resultant force. But there is a downward resultant force. But there is a downward resultant force remaining on. There's a downward resultant force remaining on any particle, remaining on any particle which is at the liquid surface. Remaining on any particle which is at the liquid surface. Remaining on any particle which is at the liquid surface. Within brackets, capital B. Right? Within brackets, capital B. within brackets capital B. Next point, hence, the liquid surface is, stretched downwards, stretched downwards due to downward resultant forces. 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 Next point, the tension force creates. Next point, the tension force creates. The tension force creates. The tension force creates at the surface due to. The tension force creates at the surface. The tension force creates at the surface due to a stretch. Due to a stretch is called. Due to stretch is called surface tension. Due to stretch is called surface tension. Right? Due to stretch is called surface tension. Right? Next point, use a red pen. Next point, use a red pen. Next point, use a red pen. Particles along the edge. Particles along the edge. Particles along the edge at the surface. Particles along the edge at the surface. Particles along the edge at the surface within brackets in contact with container. Within brackets in contact with container. In contact with container. Close the bracket. Are prevented going downwards. Are prevented going downwards due to adhesive force. Due to adhesive force between liquid and container material. Adhesive force between liquid and container material. Adhesive force between liquid and container material. Right. Right here. So basically regarding water and glass, because I use water and glass for the explanation, no? Right? Regarding water and glass, this is what is happening. Cohesive force between water and water is less than adhesive force between water and glass. Right? This is water and water. So that's why it is prevented going downwards, and there are liquids with opposite behaviors as well. We'll see in the coming parts. There are liquids with opposite behaviors as well. Okay, write this down as well. Now this is relevant to the explanation water and glass. Relevant to water and glass, but in the explanation I gave you the common explanation, right? Don't just frame to water and glass. This is what is happening with water and glass. The reason to use water and glass is this is the most popular two things we will be like comparing here in surface tension. I mean, as the usual liquids and containers, water and glass. Right? Take down. Now the idea is like this. Idea is now inside this bottle. Now can you see water? We have water inside the bottle. Inside the bottle we have water. Right? Now even though I can see this water surface as a horizontal surface, right? right? Even though I can see this as a horizontal surface, right? It is not exactly horizontal, right? It has a curvature. It has a curvature, right? But when the surface area increases, the curvature decreases. So that's why you will just observe this as a horizontal one. But exactly this is not horizontal. This is not horizontal. So inside this also there are cohesive and adhesive forces, right? So I'm not promoting VAT 69. Look at here, right? Look at here, water level, right? So that is what is happening. And in cases like what we call the capillary tubes are known, capillary tubes. So when that is getting thinner and thinner, we can see the meniscus and the curvature well. So therefore, in capillary tubes, you will see the meniscus with a higher curvature compared to these ones, right? Otherwise, if you have say water in a what we call a basket, so in the basket also that's there, but because of the surface area is very much higher, we won't notice it, right? It won't be sensitive to our eye. That's the thing, right? Otherwise, anywhere and everywhere that's there. But in small surfaces, that is visible to our naked eye. Right. So as the next heading, write down phenomena due to surface tension. 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 Right. Listen. Surface tension is a very small force. Huh? So usually its value is varying in like 10 to the power minus 2 values, minus 3, minus 4, minus 5. Likewise, they are very small forces. Listen, surface tension forces due to surface tension are very small. Comparatively very small forces. But they contribute in like different and very vital kind of phenomena, occurrences, right? So as the first one I also explained, this is called a liquid meniscus. No, one is formation of liquid meniscus. First one, write down one by one. These are the phenomena. And listen. The reason to give you these phenomena first is to give you an idea, because in the coming parts, in the calculations actually, in calculation parts, we will be doing calculations for most of the natural phenomena we are discussing here. That's why. Now, about liquid meniscus, we have calculations. So likewise, about raindrops, we have calculations. About soap bubbles, we have calculations. So likewise, that's the reason to explain these things first, to give you the idea about the phenomena due to surface tension, because then when you are doing a question also, you know whether which is relevant to which point of the phenomena due to surface tension. Likewise, right? First one, formation of liquid meniscus, right? Formation of liquid meniscus. Formation of liquid meniscus. Next one, second one. Listen. So you have seen that there are some, don't write, just look at here. There are some liquids, they are like spreading on surfaces like this, and there are some liquids, they are contracting on surfaces like this. No. As an example, water and glass behaves this way, and mercury glass behaves this way, right? Mercury glass behaves this way. Simply the reason to spread this liquid in the glass on the glass is adhesive force is greater than cohesive force. Here, the reason to contract the liquid is cohesive force between mercury and mercury is greater than the adhesive force. So therefore, if adhesive forces and cohesive forces matter, which means that is due to surface tension. Na? Simple as that. Any phenomenon due to surface tension can be explained using adhesive forces and cohesive forces, because surface tension is due to intermolecular attractions. No? So therefore, any phenomenon due to surface tension can be able and should be able to explain using adhesive and cohesive forces. Right. Second one, write down. Second point. Spreading water on glass surfaces. Spreading water on glass surfaces. Spreading water on glass surfaces and contracting mercury on glass surfaces. And contracting mercury on glass surfaces. No need to take this down. I'll give you the diagrams later. Right? First, let's list down the phenomena. Right. Third one. Right. You have seen water. Water again, what we call rain droplets, water droplets or rain droplets. Basically, rain droplet has a spherical shape, no? Right? Spherical shape. Not exactly spherical, but spherical. Right? Shape water droplets. Right? So water droplets has this kind of a shape, no? Right? And when it falls on air, the reason is, now you can understand. The reason is, this is the water droplet. Right? The reason is, cohesive force between water and water is greater than adhesive force between water and air. So therefore, it get contracted. So therefore, drops in the sense water drops, liquid drops, rain drops, they are also due to surface tension. Next one. Spherical shape of, right, list down, spherical shape of water droplets. Spherical shape of water droplets. Slash raindrops. Okay. Listen. Anyone, can you explain me the difference between a drop and a bubble? Anyone can explain me the difference between a drop and a bubble? Like we have water drops and water bubbles. We have, what's the difference between a drop and a bubble? Anyone? Quickly. No idea? Quickly. So I think you know. Common sense, or what we call general knowledge, might be. Drop and a bubble. In Sinhalese, binduak. Watura binduak කියලා කියන්නේ. Watura binduak. And watura මොකක්ද දන්නේ? බුබුලක්. Watura බුබුලක් සහ බින්දුවක්. මොකක්ද වෙනස? What's the difference? A drop and a bubble. Anyone? Surface tension. Both are spherical. I mean, both have a surface tension. I'm just asking. What's the difference between a drop and a bubble? No one? Common sense. Common sense or general knowledge? Not physics anyway. I mean, drop and a bubble, right? But for surface tension, we will need the difference between those two. That's why I'm going to explain, right? But you should know. One last chance. So at least you can guess it. You can guess, right? Doesn't matter whether it's correct or wrong. Just guess it. Any thoughts? Online in the sense where on YouTube or Zoom. Bubble is lighter. It is true. But that is not the thing that it segregates the bubble and the drop. Ayyo, dannadda. Then were you thinking that a bubble and a drop is same? Yeah, now I got the correct answer. I hope you didn't chat GPT or Google. Right. Okay, it's correct. That's the correct answer. A drop contains liquid. Drop is containing the liquid, no air inside. In a bubble, right, what is inside is an air medium. Right? In a bubble, there is an air medium inside. Right? In a bubble, air medium inside. That's the thing. That's the difference. Huh? Drop. Again, that is only the liquid in the drop. That is only the liquid. But in a bubble, there is a air medium inside the bubble. There is an air medium. Air bubbles or soap bubbles, water bubbles. Right? Okay. Next point. Next point. Next point. Formation of right, formation of soap bubbles. So you know soap bubbles, huh? Haven't you like blown soap bubbles in your childhood? You have seen soap bubbles, huh? Raise your hand if you have seen soap bubbles. Gen Z soap bubbles okay. Right, soap bubbles. Okay, formation of soap bubbles and water bubbles. Right? Formation of soap bubbles and water bubbles. Right, next one. Listen. Have you seen there are small insects, right? There are small insects, right? Now, if you feel like you need to draw this diagram along with the point, that is fine. You can take down now, right? That is fine. You can take down. So about mercury glass things, we'll be drawing those diagrams again, but not all the diagrams like one thing. 1 second. Right. Not all the diagrams like the ants, these ones insects. Right? If you need it, if you feel like you need, what you can do is you can take down if needed. Tell me, have you seen small insects like this? They are like sliding on water, and if you take a close look, they are not immersed in water. They are just on the surface of water. Have you seen? Who has seen? On water surfaces? In rivers, streams, wells? Anyone? Have seen these kind of small insects sliding on water surfaces? Haven't you seen? Are you that posh? I think this is a bio lesson. What do we call these insects? There's a term as well in biology, right? O levels are there, I guess. It's in O levels. What do we call these insects? Bio students. Water skaters. Then haven't you seen water skaters? Raise your hand if you haven't seen water skaters. Raise your hand if you haven't seen water skaters. Yeah, is inside the bubble. Yeah, it's correct. Then, what does that mean? All of you have seen water skaters. Then you have seen, no? So if you haven't seen water skaters, be vigilant when you are passing by sometimes drains or like rivers, streams, right? Lakes or water sources. Right? When you pass by, you have to be vigilant to see the water skater. That's a very small insect, small insect with 6 legs or 8 legs, something like that. 6 legs, ones who are doing bio, 6 there. I think 6 legs, right? 6-legged one, water skaters, right? So if you take a close look, and the last option, if you haven't seen, Google and see, right? What I'm referring to, that's a very small insect. And when water skater is sliding on water surface, he is not immersed. Water skater is not immersed, right? But for sure we know water skater has a weight, no? Each and every object, every particle we have in the world has a weight. Then if it is not immersed, which force is not acting here? Tell me. Which force is not acting here if water skater is not immersed in the liquid? Respond quickly. Which force is not acting here if water skater is not immersed in the liquid? Huh? What is it? What is it? So please respond. Please respond. I need answers from 26 students. 26, 27 you haven't done this yet. I mean, yeah, it is upthrust. It is correct. Put to the main chat. It is upthrust, right? Since 27 ones haven't covered the upthrust yet, that is fine. But you have done all else, no? All else are in here. Right, that is fine. Upthrust is not working here. Then who is going to? I mean, which force is going to counterbalance this mg? Which force is going to counterbalance mg? It is none other than surface tension. It is none other than surface tension. So what is happening is forces due to surface tension act on the legs, act on the legs on the skater, and the resultant acts like this, right? So likewise for small things, right? For small things, small values, surface tension is acting, right? So surface tension force can't balance our weight, right? Small skaters are, they are like, they have very small weight, like in milligrams, very small weights, right? So in such cases, surface tension acts, right? So that's why they can slide in faster speeds, right? You have seen it, no? Our water surface again, like they are very fast, because they are sliding on the surface. Okay, next, write down small insects like small insects like water skaters, sliding on water surfaces, small insects like water skaters sliding on water surfaces, right? Sliding on water surfaces, right? So why there's no upthrust or normal reaction? There's no normal reaction anyway, because upthrust is the resultant of all reaction forces acting on all surfaces of a body. That is how upthrust is defined. And the reason to have no upthrust is U equals V rho G, no? Right? U equals V rho G, where V is immersed volume. V is immersed volume. There's no immersed volume here. Right? Number four. Now you have to raise your hand. You have to raise your hand. Have you seen small metal objects like blades, needles are floated on water surfaces? Anyone has seen blades or small blades or needles are floating on water surfaces? Is there anyone who has seen or who has done that experiment? No one? Small blades big blades, those ones, big blades, the small ones, maybe like this, these ones, what we are putting, what we are replacing in our like razors and everything, like this one. No one? Then you should see at least today, right? You should see at least today, right? This is the thing. Now, even though they are metal, right? They are metal, and in terms of the density of metal is higher than density of water, but yet they are floated, right? On this side, not the sharp side, right? Not the sharp side. If you put the blade like this, assume this as a blade. If you keep the blade on the water surface like this, not like this, not like this. If you keep it on the surface like this, right? Like this, it will float. Right? and it is not going to immerse. It is not going to immerse. It is floating. Again, the reason is that weight is counterbalanced by surface tension. Right. Next point. Small metal objects like small metal objects like right, small metal objects like blades float on water surfaces. Blades float on water surfaces. Right. Next one. We have two other phenomena called, I think you have seen this, on capillary tubes. When that is put onto a liquid, the liquid is rising up like this. That is called capillary rise. And for some liquids like mercury, they get depressed like this. That is called capillary depression. Right? Both are due to surface tension. Write down capillary rise and capillary. Right? Capillary rise and capillary depression. 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 Right. And another example is, have you ever thought this? Have you ever thought about this? What? This one. This one. See? So this is the tube of a ballpoint pen. This is a tube of a ballpoint pen. Right? Now, even if I hold this in this direction, the open side downwards, this amount of carbon is never going to flow downwards and never going to go out. It is never going to go out, right? So you can try this out by keeping the pen upside down like this, but it is never going to go out. But for sure we know carbon has its own weight, isn't it? Carbon is a material. So carbon has its own weight. That mg of the carbon is balanced using the adhesive force between plastic and carbon. Right? Surface tension is very small forces, right? But it's playing very handy roles. See? Handy roles. Something like that. Next point. Forces acting on carbon tube. Sorry, carbon. Forces acting on carbon in forces acting on carbon in tubes of ballpoint pens, or pens, let's say, on tubes of ballpoint pens. Right? And another example is this is an what we call the oil lamp. This is an oil lamp. So when we light up oil lamps, right? When we light up oil lamps, right? When we light up oil lamps, right? So with oil, so oil is here. When we light up oil lamps, have you ever noticed that even if you put a new, what do you call this actually? I can't remember the term. What do you call this? wick. Thanks. Right. So even though this is a brand new wick, that we put in just now, right? So once you light it up from here, have you noticed that the oil is coconut oil or whatever the oil that you have put in here is like gradually coming towards the tip of the wick once you have lit it up. Have you noticed it? So when you are lighting this up, this might be dry, but after some time, this is wet. This is wet with the oil that you have put in. Anyone who has noticed it? At least whether you have light up lamps. Ranuti, yes. Only one? Are you kidding me? Okay, right. So now after today at least, so look at those things with that vigilant and the physics eye, right? Then you will notice these things. You will notice these things, right? So once this is lit up, what is happening is the oil particles, oil molecules are gradually coming towards the tip like this, right? So that is also because of the adhesive force between the wick and the oil. That is because of the adhesive force between wick and oil, another phenomenon of surface tension, right? So likewise, they are like minor things, simple things, but see, that is how surface tension has contributed. So simply now what I listed here was, what I listed down here was main examples. There are more, there are like plenty, not more, there are plenty, right? So always you should be able to think of a scenario with that physics eye, with that physics perspective, right? And if you can explain a scenario using cohesive forces and adhesive forces, right, you can always put that under the bucket of surface tension. Correct? Okay, mention this last one in the list. Rising oil towards the tip of wick. Rising oil towards the tip of wick in oil lamps. Towards the tip of wick in oil lamps. Right. Next heading, write down angle of contact. 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 Look at here. Look at the board. Look at the board. When a liquid is in contact with another surface, when a liquid is in contact with another surface, right? When a liquid is in contact with another surface, right? So it will be like this if there is a spreading liquid, and it will be like this if there is a contracting liquid. It will be like this if it is a contracting liquid, right? Angle of contact means, listen, right? Angle of contact means if we draw a tangent at the contacting point, see, if we draw a tangent like this at the contacting point, so from this side also you can draw the tangent like this, the angle measured between, right, the wall or the surface and the tangent through the liquid, like this, say alpha, right? Alpha, that is called angle of contact. Now in this kind of a liquid, the tangent at the contacting point is like this. Then angle measured from this wall to tangent through the liquid, that is called angle of contact. There is a small kind of an inclination at that point now, right? Then angle of contact is defined as, because there are two angles you can measure from either sides. No, angle of contact is the angle between, right, wall of the container and the tangent drawn at the contacting point through the liquid. Through the liquid is a keyword. Through the liquid, right? Okay, now as an example, this is like wood and glass. As an example, this is like water and glass. This is like mercury and glass. This is like mercury and glass. This is like mercury and glass. Okay. First write down with a red pen. First write down below with a red pen Nah? The angle measured. Write down. The angle measured. The angle measured. I have noticed that. Good. Good. Sorry, I missed it. Huh? Very good. Write down in red the angle measured between surface and the angle measured between surface and tangent drawn surface and tangent drawn surface and tangent drawn surface and tangent drawn at point of contact at point of contact at point of contact through the liquid through the liquid through the liquid through the liquid is defined as angle of contact. Right, through the liquid is defined as angle of contact, and underline no highlight through the liquid. Underline no highlight the word through the liquid. Through the liquid. Okay, now take this down. Take this down. Take this down. Right. Okay, write down below. Write down below the diagrams. For liquids like, for liquids like, for liquids like, for liquids like water with glass. For liquids like water with glass. For liquids like water with glass has an acute angle of contact. Has an acute angle of contact. Not cute, acute. Right? Has an acute angle of contact. Has an acute angle of contact. Next point. For liquids like mercury with glass. 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 For liquids like mercury with glass has obtuse angle of contact. Has obtuse angle of contact. Right. So simply idea is like this. Right. If angle of contact is an acute angle, right, such liquids are called spreading liquid. Such liquids are called spreading liquids. Right. If angle of contact is an obtuse angle, right, obtuse angle, such liquids are called contracting liquids. Contracting liquids. Right. Take this down. Take this down. Okay, now listen. When a surface is well cleaned, when a surface is well cleaned, angle of contact reduces. When a surface is well cleaned, angle of contact reduces. For our calculations, if a surface is well cleaned, we will consider right angle of contact as 0 because it is reducing and is coming to a very smaller value, right? So in our case, we will be neglecting the value, right? So in reality, that is coming to a very small value. For us, for the ease of calculations, if a surface is well cleaned, we will consider as angle of contact as 0, directly as 0, right? Next point, write down with red pen with an asterisk mark in red with an asterisk mark, write down angle of contact becomes 0. Angle of contact becomes 0. Angle of contact becomes 0 if a surface is well cleaned. Angle of contact becomes 0 if a surface is well cleaned. Angle of contact becomes 0 if a surface is well cleaned. Angle of contact becomes 0 if a surface is well cleaned. Why does it decrease? Reason is intermolecular forces between that particular surface and the molecule of the material will be decreased, right? Because of the cleaning. Because always surface tension forces in dirty surfaces is higher, right? Dusty surfaces, dirty surfaces, surface tension is higher, right? And about cleaning, listen, about cleaning. So we will have to deal with two types of materials here to clean. One is obviously glass materials, right? The other one is metallic materials, right? So there are like defined procedures or defined steps when cleaning a glass and a metal. About cleaning a glass, I think you know from chemistry. What are the basic steps of cleaning a glass container? What are the basic steps of cleaning a glass container? Quickly. So as students who are doing chemistry, right? You have to answer, you have to respond, right? Cleaning a glass surface. So basically we have 4 steps when cleaning a glass surface in labs. What are those? Anyone? Anyone has been to chemistry lab? I'm just asking. Right? Anyone has been to chemistry lab? Right. Then before starting any experiment in chemistry, so usually what we are doing is you are washing or cleaning, let's say you are cleaning beakers and test tubes, those things, no? What are the basic steps you use? Right? Doesn't matter whether it's correct or wrong, just tell me what you know. That's enough. Then you can fill the gaps if anything. And yeah, washing with clean water. That is one of the steps, correct. What else? Drying. That is also a step. Good. Now, out of these 4, 2 steps are done. What else? What else? YouTube beg of the anyone? Rinsing multiple times. Wash with acid and base. Okay. It's done. It's done. That's it. So there is a particular order. There is an order, right? So in that order only we should do it. In that order only, right? First, it should be washed with the base, right? Now, when you are writing these things in physics, right? These questions are kind of very frequently asked when it comes to physics questions, right? Don't write it as a base. You have to write the name of the base, right? Most popular or the famous base solution that we, not the solution, base we would base solution we use in our labs is sodium hydroxide, no? So likewise, with the name we will mention it, right? Okay, write down. Cleaning a glass surface. Cleaning a glass surface. So that's how teamwork works well, right? So I got like 4 steps by 3 or 4 students, right? So likewise, you should be able to do teamwork. That's a good thing. That's a good sign, good thing. And once you are in universities, right, teamwork is a must-have skill you should have, right? Because there are no any like what we call isolated things or kind of that we can do something alone, isolated from the group or the batch. There are no such things in universities, right? Always teamwork, group work is encouraged there, right? Okay, first one, write down washing with sodium hydroxide. Washing with sodium hydroxide. මේ ICD කරන්න sodium hydroxide දන්නවද? ICD students, do you know sodium hydroxide? Right, that is not a part, not a component of a computer. Sodium hydroxide, HCl all දන්නවනේ. I think you have had in O levels, right? First one, sodium hydroxide. NaOH. Washing with sodium hydroxide. Washing with sodium hydroxide. Second one, washing with HCl. Washing with HCl. Washing with HCl. Right? Third step, washing with distilled water. Washing with distilled water. Washing with distilled water. Right? Distilled water. Washing with distilled water. And last but not least, well drying. Well drying. Well drying. Right? These are the 4 steps of cleaning a glass surface. Well drying. Well drying. And then write down cleaning a metal surface. Cleaning a metal surface, right? To clean a metal surface, there's only one thing to do. There's only one thing to do to clean a metal surface. What's it? Any idea? I mean, any thoughts? How to clean a metal surface? How to clean a dirty metal surface? There's only one thing to do for a metal surface to clean it up. Anyone? Wash bottle. Wash bottle usage. Yeah, wash bottle that contains distilled water. That contains distilled water. Well, I think you haven't done about cleaning metal surfaces in chemistry, right? To clean a metal surface, the only thing we can do is heating the metal surface to a high temperature. When the metal is heated, it gets clean, right? It gets clean when it is heated, right? When it is red hot, red hot, when it is red hot, when the metal is red hot, when it is heated up to the red hot state, that is clean, that is well clean, right? Write down below, cleaning a metal surface, write down heating metal up to a higher temperature. Heating metal up to a higher temperature. Heating metal up to a higher temperature. Right. As an next heading, write down next heading, equation of surface tension. Write down equation of surface tension. Equation of surface tension. Equation of surface tension. Equation of surface tension. Right. Listen. Right. So here, this is where you are going to see the general equation or the basic equation of surface tension. And there are more equations in the coming parts. Right. This is a general equation for surface tension. And for here in physics, we don't have to prove this equation, right? We just need to use the equation. Basic equation is F equals TL. Write down the equation and highlight F equals TL. And we are going to introduce these terms F, T, and L. Write down the equation F equals TL. F equals TL. F equals TL. And another reminder, 26 batch students who haven't uploaded, who haven't submitted this week's MCQ paper yet, right? I have extended the deadline up to today midnight, up to 12 a.m., right? So make sure that you are doing it before today midnight, right? Okay, F, write down F. Force due to surface tension. 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 T, coefficient of surface tension. Coefficient of surface tension. Coefficient of surface tension. Coefficient of surface tension. Coefficient of surface tension, that is also called surface tension. Two things, coefficient of surface tension slash surface tension. Coefficient of surface tension slash surface tension, right? L is one of the most important variables here, right? Parameters here. Introduce L. Contact in length. Introduce L. Contact in length. Of liquid. Contact in length of liquid. Contact in length. That's a length. Contact in length of liquid which is open to atmosphere. Contact in length of liquid which is open to atmosphere. Contact in length of liquid which is open to atmosphere. Contact in length of liquid which is open to atmosphere. Contact in length of liquid which is open to atmosphere. Contact in length of liquid which is open to atmosphere. Right, okay. Now, listen. A small task. Small task. Using the equation, find units and dimensions of surface tension quickly. 1 minute. Find units and dimensions of surface tension and send your answers. Find units and dimensions of surface tension and send your answers quickly. Units and dimensions of surface tension. Units and dimensions of surface tension. Yadrushini, how about Gampol area after the storm? Not the storm actually, the low pressure thing. Was there an increase in winds or rain? Anything? I need SI units, right? Don't find the derived units, right? So always when I say a unit, that refers to SI, and please put to main chat. Right? Please put only the main chat in Zoom, on Zoom. Otherwise, it goes to that separate chat box in this new update. Yeah, see, surface tension is F over T, no? Sorry, F over L, no? Then units of force over units of contact in length. Force is measured in newtons. This is measured in meters length. Then unit is Nm minus 1. Newtons per meter. Nm minus 1. Nm minus 1. And dimensions of force over dimensions of length. Dimensions of force is mlt minus 2 over L. L to L cancels. mt minus 2. mt minus 2. mt minus 2. Right? Nm minus 1 and mt minus 2. Nm minus 1 and mt minus 2. Right. So I see most of you have got the correct answers. Good. Good. And tell me another question. There is another very popular quantity we have in our syllabus, and you have already covered. I mean, 26 students have already covered. Right? What is the physical quantity? Has same units and dimensions that we have already had. What is the other physical quantity in our syllabus which has the same units and dimensions? They are like very popular questions when comes to MCQs. There's another very popular one. There's another popular one. There's only one. Right? What is that quantity which has same units and dimensions as surface tension? Quickly. Normal conditions. Okay, that's good. You'd be able to say it out loud. What is it? A popular one. A very popular one. See, I gave you a hint. Very popular one. This is the 30th week before the exam for 26 students. 30th week ahead of the exam. No one. Right? That is spring constant. That is spring constant. See, same type of an equation. F equals kx. Force equals k times x is a length. See, force equals t times L is a length. Same type spring constant. Write down below with a red pen. Write down below with a red pen. Both spring constant and spring constant. Right, springs. Both spring constant and surface tension has same dimensions, same units and dimensions, has same units and dimensions, has same units and dimensions, has same units and dimensions. Right? They are same. Keep them in mind. Has same units and dimensions. Okay. Another question. Is surface tension a force? Repeating again. Is surface tension a force? Or does surface tension a force? Yes or no? It's a binary question. Does surface tension a force? Yes or no? Yes or no? Quickly. Okay, let's do this way. Then I can easily see the count. Raise your hand if you say yes. No. If you say no, raise your hand if you say no. First no. Raise your hand if you say no. What I'm asking is whether surface tension is a force or not. Only 3 says, 4 says no. Only 4 says no. What about the others? 4 says, okay. No. See, then you have dimensional units here. No? You have units and dimensions here. See, dimensions and units are different from the force. Surface tension is not a force. See, when surface tension is multiplied by this contact in length only, it becomes a force. Right? So therefore, that's a small difference. Even though we say it's surface tension is not a force. This is the force, that is force due to surface tension. Right? Surface tension can matter. Surface tension means T. Right? Coefficient of surface tension is called surface tension. That is not a force. Write down below with the red pen again. Surface tension is not a force. Surface tension is not a force. Right? So even though it says, the word says surface tension, right? Coefficient of surface tension is not a force. Make a force. This is the force due to surface tension. Right? Keep using red. Surface tension is not a force. Surface tension is not a force. Surface tension is not a force. Right. Write down as the next heading, definition of surface tension. Next heading, definition of surface tension. Next heading, definition of surface tension. Definition of surface tension. Write down definition of surface tension. Write down the equation and subject surface tension, because if we are to define something, first of all we have to subject that term. No? Write down the equation and subject surface tension. So we know F equals TL. Then surface tension is given as F over L, given by F over L. Right? If dimensions are different, we know we are defining this as unit terms. Right? Unit terms. Right? Example is, since rho equals MOV, density is defined as mass per unit volume. Density is defined as mass per unit volume. Mass per unit volume. Always denominator terms will be considered as unit terms. Now this is basically a force per unit length. No, basically this is a force per unit length. Right? The other rules when defining something is, if any quantity is divided by time, that is defined as a rate, and if they have same units and dimensions, such quantities are defined as ratios. Those are the basic rules when defining something. Now here, right, they are different in dimensions. No, so therefore this is a force on unit length or force per unit length. Force per unit length. So there are some keywords to be coming. So with the keywords I will explain you the definition. Right? But basic idea here is this is a force per unit length. Okay. First, write up to here. A equals F over L. And write down the definition in red. Write down. Perpendicular force. Write down. Perpendicular force. Acts on. Perpendicular force acts on a unit length of an arbitrary line. Unit length of an arbitrary line of any shape, drawn on a liquid surface. Drawn on a liquid surface. Drawn on a liquid surface at constant temperature. At constant temperature. At constant temperature. At constant temperature is defined as is defined as is defined as is defined as coefficient of surface tension. 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 Right. And from the definition, you better highlight these keywords. One is perpendicular force. Right. There are three keywords here in the definition. One is perpendicular force. Highlight to underline. Highlight to underline these keywords. Right. They are the must-have words in your definition. Once the definition is asked. Right. Perpendicular force. And then arbitrary line of any shape. Arbitrary line of any shape. Keyword. Arbitrary line of any shape. Then constant temperature. Constant temperature. Those are the keywords. Constant temperature. Right. As the next heading, write down next heading. Next heading. Variation of surface tension with temperature. 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 Okay, so this is an experimental result, right? So you won't do this experiment in the school laboratory, right? This is an experimental result. What you should know is this only. This is when temperature increases, surface tension decreases in an increasing rate, right? When temperature increases, surface tension decreases in an increasing rate, right? Okay, let's take this down. Now this arrow is because I have drawn the graph to the increasing direction of theta, increasing direction of temperature, right? Then the graph goes from here to here in the increasing direction. That's why we put these arrows on the graphs. Okay, write down below with a red pen. Write down below with a red pen. When temperature increases, write down below. When temperature increases, surface tension decreases. When temperature increases, surface tension decreases in an increasing rate. In an increasing rate. In an increasing rate. In an increasing rate. Right. So let's see a few examples. How should we write this force from surface tension, right? So let's see few examples, right? Example 1. So as examples, we'll discuss few examples before moving on, right? Example 1. Example 1. Example 1. Write down here. A coin of radius r. Write down here. A coin of radius r. A coin of radius r. Coin. A coin of radius r floats on a coin of radius r floats on water. Floats on water. A coin of radius r floats on water. Right. Why is there theta? Theta is the standard symbol of temperature, relative temperature. Absolute temperature is capital T. Relative temperature is theta. Right? Take this down. Take this down. Diagram. Take down the diagram. Take down the diagram. Right? This is a coin. And here you can see I have drawn this liquid with this curve, with this small curve. Right? So in surface tension, when the diagrams are given, these curves are also given. Right? So that's why these curves are drawn. Right? Draw it with the curve like this. Draw it with the curve like this. Because in surface tension, that's all about the stretch for surfaces. So therefore, it will be curved. That will be curved like this. Okay. See, now this is how we write surface tension. One is, listen, one is, first you have to identify the direction of surface tension, right? To identify the direction of surface tension or identify the direction of force due to surface tension, right? So basically, what you are given is a diagram, right? So if there's nothing given in the description or wherever, right? Basically, what is given to you is a diagram. So from the diagram, you can see in which direction the liquid has gone, right? Whether it has risen up or whether it has depressed, whether it has gone downwards. So likewise, you can see the direction of curvature of the liquid now from the diagram. Always that this tendency. Now in this case, the liquid has gone up. Liquid has gone up, right? Liquid has gone up. Since the liquid has gone up, right, which means force on the liquid should be upwards now, because if there is an upward motion for the liquid, right, motion in the sense is kind of an upward tendency of the liquid, right, it should be because of an upward force. Simple as that. So therefore, force due to surface tension on the liquid here is upwards, right? And this is how forces are occurred. Look at the board. Look at the board. Now, I will explain this from scratch since this is the first example. So stop all your work and look at the board. Now, along all the surface like this, the liquid is in contact now. Along all the surface, throughout the surface, the liquid is in contact. Then this whole liquid is now think three-dimensional. Yeah, coin is a circular object, and throughout the coin, right, all around the coin, the liquid is like this. The liquid is there like this with this small rise, like this, right? Then each and every point of the liquid, each and every point on the liquid. So likewise, these forces exert, right, on each and every point which is in contact. This force exert. Resultant of all these forces, right? Resultant of all these forces will be marking as F, right? So I'll be marking the resultant of all these small forces on the liquid as F, like this. So which means force due to surface tension on the liquid is upwards, that is F, right? So always we'll be writing the resultant only, right? Formation is like infinite number of, is like infinite. Formation is from infinite number of small molecules, and the resultant is F. And this equation is also for the resultant force. Right. Now Newton's third law. Now if there is a force acting upwards on liquid due to surface tension, right? We know, according to Newton's third law, there should be another mutual force acting downwards here on the system, right? Otherwise, Newton's third law is violated, no? If there is an object, if there is a force which is acting on an object in particular direction, right? There should be another mutual force, equal and opposite mutual force acting to the opposite direction. Now, force due to surface tension on liquid is upwards. Then tell me on which object I should mark the mutual force of this F. Is it on the other side of the liquid or on the coin? Where is it? The other mutual force which follows Newton's third law, right? Because any force should follow, I mean, any reaction force and action force should follow Newton's third law, right? Then, yeah, obviously it should be on the coin. So therefore, since surface tension on liquid is, now this is the surface tension on liquid. See, this is on liquid. These are the basics. Look at the board, right? On liquid, and equal and opposite acts on the coin downwards like this, and this is on coin, right? So you have to start this with the liquid, because with the diagram, what you are given is the direction of tendency of liquid, whether it's like rising up upwards or downwards. Then with that, you have to get an idea about the direction of surface tension on liquid, and exactly equal and opposite is on the object, right? Take this down before doing the calculation part. On coin, yes, correct. So for resultant, isn't it downwards for water? No, because water surface has gone up in this particular scenario, not down. Water surface has gone up. If water surface has gone down, it will be downwards. If the water surface has gone up, that is upwards. Right. Finished? Now, listen, in our usual force diagrams, right? In our force diagrams, we don't mark these infinite forces. I mean, these forces we don't mark directly. I mean, at once we mark the resultant only. Now, I mark these forces to show you how it happens, because this is the very first question, very first example, right? That's why. Otherwise, we don't mark these ones in our force diagram. On our force diagrams, at once we will be marking the resultant. Okay, so writing the magnitude is very much easier. F equals TL, no? So let's consider surface tension of this liquid as T, yeah? So we'll consider surface tension of this liquid as T. We'll consider surface tension of the liquid as T, right? TL, L is contact in length open to atmosphere, right? So before I write, tell me, what is the contact in length of this scenario open to atmosphere? What is the contact in length of this scenario open to atmosphere? Anyone? What is the contact in length which is open to atmosphere? So I need answers from your end. What is the contact in length open to atmosphere? Umaima, 2R. Tashi, 25R. Others? So likewise, please respond. What about the ones on YouTube? Any answers? What is the contact in length? And now you should be able to imagine this scenario. Imagine this. This is a coin floating on a water surface. Yeah. Then throughout this, there is in contact, right? All around this, there is in contact now, all around, right? So therefore that length is 2 pi r. Circumference. Then apply the equation. F equals T into contact in length is 2 pi r. So surface tension force here is 2 phi RT. And this is how we separate this. Then it is like on coin, F equals 2 phi RT acting downwards, and on liquid, it is also same 2 phi RT acting upwards. Got it? See how easy to write surface tension force? The only thing that you need to be mindful when writing is about this contact in length. T is anyway, it is given, no? Coefficient of surface tension. Then the only thing you have to be a little bit mindful when writing, mindful and careful when writing here is L. Right, take it down. And while taking down, raise your hand if it is clear enough. How to write force due to surface tension. Quickly. Raise your hand if it is clear how to write surface tension, force due to surface tension. Raise your hand. Is it only two? Does that mean only two, right? Does that mean the others didn't get this? Is it? So if you have any questions, you can ask, right? So if not, if it is clear, you can raise your hand. F1 liquid and on the coin. Direction of F1 liquid is determined looking at the direction of the tendency of liquid, right? If the liquid has gone up, see now from these points you can clearly see this now. The tendency of the liquid is to go upwards. That is because surface tension acts on the liquid upwards, right? So likewise, you have to start identifying it from the liquid. That is the easiest way. You have to start identifying it from the liquid, right? So if there is acting upwards on the liquid, that should be downwards on the coin. Why do we write both forces? This is as an example, right? Then you have to pick the required force between these two with your requirement when we are moving ahead with questions. Right? This is just for the explanation. This is an example. So mostly we will need only the force acting on the object, because usually we are applying equations for the objects now, right? I mean for the questions proceedings, we will only need the force acting on the object. To find the force acting on the object, first of all, you should know the direction of force acts on the liquid. So that's why we started from the liquid. Okay, is it clear enough now? So you can ask if you got any confusions. Right? You can ask if any confusions. Two phi r, yes, good. 2 phi r, yes. Right. So I'm asking again because this is the first example we discussed from surface tension. So please raise your hand again if it is clear. 5, 6. Is it 6 still? Is it only 6 yet? Okay, right. All right then. Write down below with a red pen. Good. Okay, good. Put it down. Good. Write down below with a red pen. Force on liquid and force on object. Force on liquid and force on object. force on liquid, and force on object, force on liquid and force on object, force on liquid and force on object are equal and opposite forces, 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 are equal and opposite forces within brackets action and reaction, within brackets action and reaction, within brackets action and reaction, which follows, which follow Newton's third law, 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 which follow Newton's third law. Right. Okay. Example 2. See, look at here. Example 2. About enrollments. Yeah, I actually didn't explain. Right. About the enrollments, simply what you can do is, you can visit the website. You can visit the website tsphysics.lk, right? And then create the account, right? Create your account, create your own account. And once the account is created, you can see all the available classes, right? And go into the respective class. Now it is with the title as reverse class. Click on this and go into this, right? So once you go in, it will be you will be asked about an enrollment key. As the enrollment key, you can use this, right? This is the enrollment key. Capital P simple S at capital P H Y, capital P simple H Y, capital R C26, right? So I have put this on the group as well if you are already in the group, right? If not, this is how you can do. And if you need any clarifications, any assistance, you can contact this number. WhatsApp. Right? You can contact this number on WhatsApp. You can contact this number on WhatsApp. Right. So basically, this is what you have to do. And next week onwards, listen. Next week onwards, this won't be live on YouTube, no, right? Then you have to join to the class through the website, right? So therefore, you can complete 2 enrollments before the next week, right? Okay. Example 2. Example 2. Write down a cube of, a cube of side length x, a cube of side length x, a cube of side length x, a cube of side length x is half immersed, is half immersed in water, is half immersed in water, right? Is half immersed in water, is half immersed in water, right? You can take this down. You can take this down. For you to see the liquid clearly, so I'm drawing this with this perspective, right? For you to see the liquid properly. That's why. Right. So this is floated on the liquid, half immersed. And this is how you will see the liquid surface here. So imagine this three-dimensionally, yeah. Imagine this three-dimensionally. So imagination plays a role here. Imagination plays a role here because we can't draw 3D diagrams on our sheets, on our boards, right? Then if there is something happening three-dimensionally, then you have to imagine it. You have to imagine it in your head. That's the key here. That's the key. Okay, try this, and write the directions and magnitude of force due to surface tension on liquid and object. Write down force due to surface tension on liquid and object. Send your answers if you got answers. Send your answers. I gave you side length as x. I gave you the side length as x. This is a cube, no? Then all depth, height, length, everything is x. Any answers? And during this month, I'm planning to have the optical instruments seminar, right? During for 26 batch, during this month, most probably, we'll be having the optical instrument seminar, right? Dates are not fixed yet. I'll inform the details. Keep in touch. Yeah, any answers? Any answers? 40x downwards on water, 40x upwards on object. On liquid, 4xt downwards, on cube, 4xt upwards. What else? Okay, let's see. Right, let's see. Okay, so to decide the direction, right? Decide the direction. Imagine this and check the diagram. What is the direction of moving tendency of water, upwards or downwards? You should be able to imagine this three-dimensionally, right? What is the direction of moving tendency of water, upwards or downwards? Right? Now, if you can't see this way, now I draw this for the better understanding, right? Otherwise, if you are more familiar with this type of a diagram, right, that is up to you, that you can draw, right? So in this kind of a diagram, this is how you will see this on this kind of a diagram. Same, right? Same, like this. Then liquid has gone up. So surface tension on the liquid is upwards. Equal and opposite is on the object downwards, right? Then magnitude is F equals TL. Then F equals TL. L is contact in length is all four sides like this. One side is X, then all four sides 4X, right? Then final answer F equals 4TX, right? 4TX. And this is upwards on water, upwards on liquid, upwards on liquid, right? And this is downwards on object, right? So I see in some answers now you have messed it up with the direction, right? Direction is just by looking at the direction of moving tendency of liquid, right? If this diagram is more clear, you can take this down, right? So this direction is upwards, right? This is the horizontal liquid and here it has gone upward. This is the horizontal liquid, it has gone upwards. Imagine this three-dimensionally. Now, if you look through this from this vertex side, this is how you see it, right? Next one, example 3. Example 3. Example 3. Write down example 3. Write down a hollow cylinder. Write down a hollow cylinder. Example 3. A hollow cylinder. Ask if any confusions, right? A hollow cylinder of internal radius simple r. Of internal radius simple r. Of internal radius simple r. And external radius capital R. And external radius capital R. Is immersed on water. 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 Okay, look at here. A hollow cylinder. So this is the hole in the cylinder. This is the hole in the cylinder, right? This cylinder is immersed in water. Right now, from this side also the hole is there. It will not be visible. that is behind. So this is how it is, and the liquid is like this. And internal radius is simple r. External radius is capital R. Right? Okay, try this. Try this. Send your answers. Any answers? Right. Now this hole is throughout. Now this part cannot be seen. No, this hole is throughout this. I mean from top to bottom. This hole is throughout from top to bottom. Hole is throughout from top to bottom. Right? For water 2 pi capital R T upwards. What else? F equals capital R minus simple R T. What else? Any different answers? Send your answers. Send your answers. This is just a matter of your imagination, right? Because L is the contact in, I'm repeating again, contact in length of liquid which is open to atmosphere. Contact in length of liquid open to atmosphere. L. Contact in length of liquid open to atmosphere. That is L. Contact in length of liquid open to atmosphere. Contacting length of liquid open to atmosphere. That's L. That's L. So imagine. So this is all about imagination, right? So think where the liquid is, think where the water is, or the liquid is going to be in contact, because L is the contacting length, no, and it should be open to atmosphere. 2 phi capital R plus 2 phi RT capital R plus simple R. Oh my god, 2T phi capital R minus simple R. Right, let's see. Okay, my first question. Tell me whether this water goes into this hole. Does this water goes into this hole or not? Does this water goes into this hole or not? It goes in. It goes in. This is an open hole. This is an open hole throughout the length, right? Throughout the height of the length, right? So it goes in. It goes in. Then if it goes in, look at here. Look at here. That's the only imagination you needed. So if it goes in, now from this outer surface, it is in contact throughout the outer surface, around the outer surface. And when water goes in, from the inner surface also, the liquid is in contact, right? So there are two surfaces now on the same object where the liquid is in contact. There are two surfaces. Then F equals TL, T times total length. From the outer surface, contacting length is 2 phi R. Right? From the inner surface, contacting length is 2 phi simple R. Right? Then F equals, take 2 phi out, 2 phi T capital R plus simple R. Right? And this force is acting upwards on liquid and downwards on object. Right? So this force acts upwards on liquid, downwards on object. See, that is all about imagining something, thinking about this, how this actually happens, right? And this thickness is not going to be a length. That is not a length. And moreover, thickness is not open to atmosphere from the bottom side, right? So imagine this. Once you put this thing into water, from outer surface also, water is in contact. And water goes in, no? Water goes in. Then from the internal wall of the internal wall of the inner hole, water is in contact. Then this surface and the inner surface. Raise your hand if that is clear. Raise your hand if that is clear. Right, good. So that's how you should imagine, right? That's how you should imagine. If this hole was closed, only the outer surface. If this hole was a closed one, now it is an open one, then both surfaces are in contact. Okay, let's move on. Now again, we have a small proof to do, right? A proof of an equation. And we will practice more questions on this type about riding force on the next day, right? Now, these just few examples to you to give an idea. Right, let's move on to next theory part we have. Next heading, write down determination of tension exerts. Write down determination of tension exerts on a closed loop. Determination of tension exerts on a closed loop of string. Tension exerts on a closed loop of string. On a closed loop of string. On a soap film. Films are also called membranes. On a soap film or soap membrane. Soap film or soap membrane. Okay, listen. Listen, another very interesting idea, a nice idea, and a different idea. Listen, listen. Stop all your work and listen. Right. So first thing is creating a soap film. Soap film is a soap membrane. Soap membrane or soap film means, right? That is what you see uh, on a frame. It can be either circular or rectangular, whatever it is, right? Now, in this case, let me consider a rectangular frame. Now, say this is, look at the board. Say this is a rectangular. This is a rectangular wireframe. Rectangular wireframe. If you immerse this wireframe in a soap solution, if you immerse this wireframe in a soap solution and if you take it out, have you seen that a soap film is going to remain on the frame, in between the frame, on the frame like this? Have you seen this? Oh, can you imagine this about the soap film? That very thin layer is called the soap film or the soap membrane. The idea is there, no? Films means very thin layers, no? So that thin layer is called the soap film, right? Can you imagine, no? So you have to dip this, right? Immerse means you have to dip this in a soap solution and take out. Once it is taken out, this soap film will be on the wireframe, right? Then next step is, see, this is how this thing is created. Look at the board. Next, what we have to do is, now on this film, look at the board. On this film, a closed loop of a string. Now this is the film, no? On the film, a closed loop of a string, a thin string, is carefully kept on this. Is carefully kept. Right? Otherwise, if you like try to do it quickly, this soap film will be broken. Right? It will explode. It explode, you know. I think you have seen this. Like soap bubbles, soap film is also exploded. So therefore, like carefully, slowly, you have to keep this closed string on the loop. Right? When that is kept on the the loop kept on the soap film, due to soap, between soap and string, there are adhesive forces, no? Adhesive forces means surface tension. Then this is how surface tension forces are going to exert. See? Now likewise, all around this, there will be surface tensions. All around this is not the resultant. And soap film is also inside the string as well, no? Then inside also, it will be here, it will be there like this. From the inside also. So all around this, it will be like this. All around this, it will be like this. Right? Surface tension, forces due to surface tension. And one more important thing about a soap film is, can you imagine that since soap film is a very thin layer, from its top surface also, that surface is in contact with air, right? And from the bottom surface also, it is in contact with air. That's a thin layer, no? So therefore, unlike a thick liquid, in soap film, since there is a very thin layer, from both sides, it is in contact with air. Since it is in contact with air from both sides are open to atmosphere. Therefore, this same thing is going to happen at both surfaces, right? Both surfaces in the sense, top surface and the bottom surface of the very thin layer. So therefore, when we write surface tension on soap, without using just T, right? We will be replacing this T with 2T to consider both sides, right? We will be replacing this T with 2T to consider both sides. I will give this in the note. So don't write this. I will give this on the note. So therefore, these surface tensions actually represent both sides since there is on soap. So that's why I'm marking it as 2T for my understanding and the identification. Right. Raise your hand that if that idea is clear. Why we have to use 2D instead of T? Raise your hand or tell me if I need to explain it again quickly. Explain again. Right. Listen. Now you should be able to imagine. You should be able to imagine. Now the soap film is something like this, a very thin layer. Right? It's a very thin layer. Very thin layer. Now string is kept on this. The string is kept on this. The string is also thin, and soap film is also thin. Right? So therefore, now from the top side also, that soap film and the string is open to atmosphere. From the bottom side also, if you look like this, if you observe like this, from the bottom side also, that string and the soap film is open to atmosphere. Because that is a thin layer, no? Unlike a thick layer. Soap film is not floating. That is not floating. That will be just in the inside. I mean, that will be inside the soap film as it is open to atmosphere from both sides. Because soap film is like, that is not thick even as 1 millimeter. You can have 1 millimeter, but nah, it is like a very small thickness. Soap films. Like 10 to the power minus 3, 10 to the power minus 6 centimeters, okay? Something like that, around that. Right? So therefore, that is open to atmosphere from the top and the bottom. So if there are open surfaces, right? If there are open surfaces, right? They are open surfaces, no? Open to atmosphere, no? Open surface again, surface tension there. So therefore, surface tension exerts on both surfaces because both surfaces are open. Right? Now, if you go back to the initial explanation of surface tension remains only on the surface. Now, on the soap film, there are two surfaces from the top and the bottom. Both are open to atmosphere because the film is like this. Around the frame, the film is like this. This is the film. Methaninuth open. From both sides, it's open. Is it clear now? Raise your hand if it's clear now. So if not, you can still ask questions. Okay, now it's clear, right? All right. So don't write this. I will be giving this on the note. Right. Next step. Look at here. Next step. Now, if needed, you can try this at home. Right? If needed, this is something you can try at home, and you should have some kind of a patience when doing this. That's the only thing. Right? You have to have patience. You can try this at home. Right? An activity that you can try at home. That is an activity you can try at home. Okay. See. Now, you have to have a needle. Listen, you have to have a needle. Get a needle. And by the needle, right? We are going to break this inner film. Now, film is divided into two now. Outside of the string and inside of the string. Right? Now, we are going to you are going to hit on this inner film, right? Something you should do like with a patience, right? You can hit this with a needle, right? So once that inner surface is hit with a needle, what happens is that inner surface is exploded, right? Can you imagine? No, now if you have the experience of soap bubbles, right? So if you hit a soap bubble, it gets exploded. Similar thing. Then using a needle, you have to hit the inner surface like this, right? And once this inner surface is hit, inner surface is exploded. Once the inner surface is hit, inner surface gets exploded. When inner surface is exploded, all the surface tension forces with the inner surface will be disappeared because there's no more inner surface, right? Then all the surface tension forces at the inner surface will be disappeared with the inner surface because there's no inner surface now. And only surface tension of the outer surface remains. And all of them are acting, see, they're acting away from this string, no, like this, outer surface, they're acting away from the string. So therefore, as the resultant impact, what happens is, now each and every point of the string is dragged outside by equal forces, by like infinite number of equal forces. The ultimate result of this is, this becomes an exact circle. this becomes an exact circle, right? You can try this at home if needed. Now, this becomes an exact circle, and only the outer film remains. Only the outer film remains like this. Only the outer film remains with these forces. Only the outer film remains with these outer surface tension forces. With these outer surface tension forces. Right? So this is not the result, and I'm just marking the individual forces. They are like 2T each. 2T each. 2T each. And it's going to form a circle, and it forms a circle. And let's assume radius of this circle as R. Let's assume radius of this circle as R. Right. So again, raise your hand if this formation is clear. Imagine, right, exploding the inner circle, inner surface, exploding the inner surface. Right? Can you please explain the arrows again? Arrows is because of the cohesive forces, and I have marked the surface tension on a string. Then on a string, by soap, on a string by soap, right? Attractions. Sorry, adhesive, cohesive. Adhesive forces, they are attractions. Then this is attracted to the soap molecule. Intermolecular attractions, right? That is where we started today. Intermolecular attractions. So because of the attraction, they are attraction forces. Any other questions? Any other questions? Or if no questions, please raise your hand if it is clear up to here, right? This is what we need before proving the equation. And if not clear, right, ask your questions quickly. If not clear, ask your questions quickly. Right? So don't raise your hand if it is not clear to you. Then instead ask a question. You can ask your doubt. So about the forces, it's clear now, no? Right. Okay. See, now, since the string is stretched, listen, since this string is stretched, now a tension has exerted on the string, no? Now in this scenario, string is not stretched, but here the string is stretched now. Since the string is stretched, it has got a tension. That is what you are going to determine now. Tension of the string, right? Tension of that loop. This is the loop. This is the loop, right? So this is what we are, here what we are going to do is to find this tension on the loop now. On the loop, so that is inside this. Tension is an internal force. Since tension is an internal force, if you consider the whole system, we are never going to see the tension. So therefore, right? So you know from mechanics how to find tensions at middle points of a string, right? Then to find a middle point of a tension, tension of a string, you have to break the system from that particular point. I'm going to do the same. So I'm going to break this. See, I'm going to break this into two. Then one half is here, like half and half, half by half. Let's break this up. Look at the board. One half is here, like this, and the second half is here. I have broken this from here. Right? And in these parts, now these forces 2T. These forces are still remaining. There are infinite number of forces. So we can't mark all. This is only for your understanding. There are infinite number of forces. So here also you have, right, same idea we do in strings in mechanics. Right, now listen, now since the loop is broken, now the tensions at the broken point should be remain as attraction forces, no? Right? So exactly what you learn in heavy strings, weighted strings. So I will consider the tension on the string as F. Then here also the tension as F. Same tension, same and opposite F. Same and opposite F. Right? Now my ultimate goal is determining this F, because F is the tension on the string now. I didn't mark it as T because I have already used T for surface tension. That's why, right? So we'll consider that as F. Okay, now take this down clearly. No need to write down this. I will explain. I will give this on the note. Right. First, these are the steps. This is step 1, step 2, step 3. Take down these diagrams. Take down these diagrams before moving on to the proof. Right. Here you have a small proof. Proof is very easier. Right. Now this explanation takes time because I have to create this imagination on your head now. Since you haven't done this, so that's why it takes time. Right. Once you imagine this once, then hereafter it is going to be nothing. Imagining for the first time is kind of taking time now. That's why I explained that way. Okay, take it down, take it down. Take down. And you can use different colors if you have like this, right? Now, these colors are for your understanding, right? Use colors. And while taking down this also, if you got any doubts, ask and clarify. And in leisure time, you can try this out if needed in leisure time. And you have to be very patient throughout the process. Okay, finished? So tell me if you have finished this, because all of you should finish this uh, in order to start the proof here. Put a thumbs up if you have finished. Put a thumbs up. Thumbs up if you have finished. Is there only one? Be quick. Be quick. Take it down quickly. Take it down quickly. Okay, see, oh, the time is enough. It is no? Right, see. Now, I'm going to consider the horizontal equilibrium of 1/2. See, by considering horizontal equilibrium of 1/2, by considering horizontal equilibrium of 1/2. Look at the board. Look at the board. And here also you are going to learn a new idea here in this proof, and that same idea will be used in other proof in surface tension. Right? This is a new idea, and listen carefully. Right? Here you are going to learn a whole new idea within this proof. Right? One is this. Horizontal equilibrium. No? Then horizontally rightward forces equals horizontally leftward forces. Right? Horizontally leftwards. And horizontally rightwards, we are sure. Now let me take this half. I will be considering this half. Let me consider this half. Right? You can consider any half, that is fine. I'll consider the left half. So rightwards we have two forces, F and F. So that is 2F. Right? Rightwards two forces, 2F. 2F. And about leftward force is going to be the resultant of all these surface tensions, no? All these forces due to surface tension, no? So let me mark that resultant as FT, right? Then the resultant leftwards is FT, right? Now this is where you are going to learn this new idea. If you have infinite number of forces, now from here to here we have infinite number of small forces, right? If you have infinite number of forces which acts in different directions, and if you need the resultant force or resultant vector, rather, this is right for all vectors, resultant vector acting along a particular direction, right? What we do is we can multiply one particular force, with the projection of the object towards that considered direction, with the projection, right? You have heard about projection in two places now. One is under projectile motion, the other is at simple harmonic motion. What is a projection? First tell me that. I'll be explaining this, don't worry. What is a projection? Projection, I have explained about projections in two places so far. Projectile motions and simple harmonic motions. That's a shadow, right? That's about a shadow. Now, I need, look at the board, I need resultant acts in the leftward direction, no? Then what I am saying is you have to take the shadow of this object in this direction like this. Now assume you have a screen here. What is the shape of the object that you are going to see on this shadow? What is the shape of the object that you are going to see on this shadow? On the screen as a shadow. Imagine, no? Imagine. Now, if you need to imagine a shadow, assume that we are going to place a light source from this side. Now, I need the shadow in the leftward direction. If I need the shadow in the leftward direction, assume that we are placing a screen here, right? It's a vertical line, a straight line. Can all of you imagine that? Make a loop. Shadow of this loop is a straight line. Is it imaginable for all of you? Raise your hand if that is imaginable. If you can imagine that in your head, right? That's going to be a straight line, right? So if you can't imagine, what you can do is take a ring or something, right? Ring name ring or like a bangle like this, bangle or ring or something, right? Get a thin one, a thin bangle, a band or something like that, right? And what you can do is, right, place a light source from this side and check the shadow that you are going to see on the screen like this. So it will be a straight line. And what is the length of that straight line exactly? What is the length of the straight line? What is the length of that straight line you are going to see on the screen? What is the length of that straight line that you are going to see on the screen? This one. That is diameter. That is exactly 2r. That is exactly 2r. Right? That is exactly 2r. That is a diameter. Okay? So if needed, you can extend the diagram like this if needed only. If needed. Right? So again, repeating again, if you have infinite number of forces, vectors somewhere, infinite, not just a countable number, there should be an incountable number of forces. Infinite number of vectors somewhere which are acting towards different directions. Right? Resultant along a particular direction, a given direction, a required direction is given by one force into projection, one force times projection through that required direction. Right? This is the same idea. Listen, this is the exact same idea you are learning learning in integration in combined maths. Right? So if we integrate this from here to here also, the result will be same. Since we can't do the integration here in physics, that's why we have converted that same idea into a projection. Right? Otherwise, if you integrate this force starting from here to here with limits from here to here, from 0 to 2r, if you integrate the force from 0 to 2r, you will be getting the same answer. Right? So I hope all 26 students have completed integration. Right? So if you know integration, what you can do is integrate 2d from here to here, putting the limits as, setting the limits as, if you are changing the angle from 0 to 180, if you are changing the length from 0 to 2r. Right? That same idea is simplified here in physics for us to use as the projection. Right? So otherwise, this is the exact thing you are doing in integration, and one of the applications of this integration is in combined maths under center of gravity, determination of center of gravity of objects using integration. Right? Same thing. Right? Now, see, now one vector is 2d, no? One vector is 2d, and the projection is 2r. Projection is 2r. Then this gives the resultant in this particular direction. One vector into projection. And always, listen, always that projection will be having the same units and dimensions of your required quantity. Yeah? As an example, now this is a force due to surface tension. We know force due to surface tension is given by E into L. So we need a length, no? We needed a length. We were seeking a length. So exactly a length is coming. So if you are seeking an area somewhere, you will be getting an area as the projection. Got the idea? So likewise, the exact correct term is coming with the projection. Right now, this is it. 2f and 1 2 to 2 cancels. F equals 2tr. So this is a proved equation. F equals 2tr. This is a proved equation for the tension exerts on a closed loop in a soap film. And this is a proved equation you can use anywhere in MCQs, structured essays, wherever, if this scenario is given, right? And this equation is valid only for this scenario, only for this scenario, only for this scenario. Soap film with a closed string, right? So this is the end of the proof, and you should know this proof from beginning to the end, right? Because this proof is asked from you to prove as well, right? There have been actually questions to you to prove this. Then, so after doing these things, right? Now, if you are doing the proof, no need to draw this one, right? Starting from here is enough. These two is not needed. Starting from this is enough. If you are doing the proof, you should be able to do this proof by your own, like this, right? You have to draw this diagram and this one and do the proof. Right, now raise your hand if it is clear, and you can send your questions if there's anything, and take this down quickly. So this is just a binary, right? So if it is clear, you can raise your hand. If it is not clear, you should raise a question. Okay, clear now? Right, take it down. Take it down. I will give you this idea in the note, right? So don't worry about this idea. This is a new idea, right? All of you are learning for the first time about finding resultant vector in an infinite case like this, right? So I'll be giving the complete note. I mean everything in the note. Don't worry. Just take this down now if you have understood. Take it down. So I'll stay aside. You can take down. And this is the screen. I mean, this is for the demonstration, no? So just think that, assume that you are placing a screen and think about the shadow projection on it. So that's why I draw the screen. That is all about imagination. All about imagination. Shadow games මොනවද play කරලා ඇතිනේ පොඩි කාලේ. I don't know whether that's the correct term, shadow game. So I don't know. So likewise, you should be able to imagine how the shadow falls. Right? Finished? Okay. Introduce terms. Introduce terms F. Introduce terms F, T, and R. F. Write down F. Tension on a string. Or write down tension on closed loop. String / closed loop. F. Tension on a string / closed loop. 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 T. Surface tension. T. Surface tension. T. Surface tension. R. Radius of loop. R. Radius of loop. Radius of loop. Radius of loop. Radius of loop. Right. Then take down the note in red pen with asterisk marks 1 by 1. Right? Using a red pen. First point. First point. Since soap is in contact. First point. Since soap is in contact. Soap film. Soap film. Since soap film is in contact. Since soap film is in contact. Since soap film is in contact. Since soap film is in contact with air. With air. With air. From both sides. From both sides. From both sides. Within brackets top and bottom. Within brackets top and bottom. From both sides. Within brackets top and bottom. From both sides within brackets top and bottom. Use 2T. Use 2T instead of T. 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 Fine. Second point, keep using red. Next point. To determine directional component. To determine directional component. To determine directional component. To determine directional component. When multiple within brackets infinite / incountable within brackets infinite / incountable infinite / incountable close brackets vectors are actin multiply 1 parameter multiply 1 parameter multiply 1 parameter multiply 1 parameter within brackets variable within brackets variable with the projection with the projection with the projection towards with the projection towards with the projection towards with the projection towards the required direction with the projection towards the required direction with the projection towards the required direction with the projection towards the required direction, right? So keep that idea very well in mind, because now within the same lesson surface tension here itself, you are going to see the same idea, you are going to use the same idea again in another proof, right? And keep the next heading written, right? So this is where we'll be starting next day. Keep the next heading written, pressure difference. Next heading, keep this written, pressure difference across a liquid meniscus. 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 Okay. Listen now. Listen. Right. So we have started. We have started surface tension today under properties of matter, and so as I told you at the beginning, now it's like 80% of the 80% of the theory parts are finished now, right? Like 80% is finished, right? Now only few parts are remaining. The remaining parts are first one, pressure difference through liquid meniscus, and then surface energy, and the last one, capillary rise and capillary depression. Like three small parts, right? And yeah, about the reverse class and the lineup in the reverse class, it will be like, now first we will be covering properties of matter, and then my plan is to start electricity, and then after electricity we will be covering electronics here, right? And matter and radiation, right? And magnetic fields. So those are the planned lessons here for the reverse class, and all of them are impactful lessons, very much impactful lessons, right? Electricity is a 20% lesson, electronics is a 20% lesson, right? And this is properties of matter 10%, and matter and radiation is going to be 10%, right? So likewise, they are very impactful lessons, right? And actually lessons, most of the students and sometimes some of the like teachers also are stuck at, because there are things, I mean there are kind of thinkings, there are kind of imaginations, right? There are things. So especially in lessons like electronics, magnetic fields, right? So sometimes students and both, I mean both students and teachers are also kind of scared to teach and learn the lessons, and students also they have a fear of taking the questions, right? So don't worry, we'll be covering everything from scratch here in the reverse class on these most impactful lessons, right? They are very much impactful when it comes to your final mark, right? So as I told you, you have to complete your enrollments before next day, right? I saw there were like considerable amount of students who were enrolled today itself, right? Today itself, if there are new ones, I mean for the new ones, if you haven't used the website before, right? If you have any, I mean, if you need any clarifications, if you need any assistance from that technical side, you can contact that number 071 618 8597, right? And you can get those numbers from my YouTube channels, WhatsApp channels, Telegram channels, or from anywhere, and feel free to contact, right? And before next week, please complete your enrollments and everything, because log into the class, join into the class can only be done through the website. Right? Okay then tell me, are you clear of everything that we discussed so far today about today's lesson? Are you all clear about everything? we discussed so far in today's lesson? Raise your hand if that is clear. Right? Raise your hand, and the ones on YouTube also, say whether it's clear or not about the lesson today. Right, clear now? Good. So as a lesson, surface tension is a small lesson, right? Surface tension is a small lesson, right? So in not more than 2 days, right? This doesn't take 2 more days, right? This will take like around 1 to 2 days of time to finish this off with all the questions. It's a small lesson. It's a small lesson. Clear? Right. Okay then. Then we'll wind up. We'll wind up the class. So this will be the fixed time for this class. Starting from today, right? 7 to 10 Saturdays. 7 to 10 Saturdays. And yes, that's it. So is there anything to clarify from my side before winding up? Is there anything to clarify from my side before winding up? Is there anything to clarify from my side before winding up? Okay, then it seems no. Right. So if no, we'll wind up. Right? We'll wind up. So stay safe and be safe. No, the storm is gone. The storm is gone anyway, but stay safe. And we are 30 weeks ahead of the exam, right? 30 weeks out of the exam. And this is a time that you should use with your maximum effort, maximum dedication, maximum effort and everything, because this is the most impactful time period, right? Most impactful time period that directly impacts on your result, final result in your whole life, right? Because A-levels will be the most competitive exam you are going to write in your entire life, right? For anyone, that's the same story, right? Local syllabus A-levels or GC A-levels is the most competitive exam here we have in Sri Lanka, right? Most competitive one. Therefore, utilize these times, this time, 30 weeks of time effectively, right? So don't waste even a single minute of this time, right? Utilize it effectively, right? So see you all in the next class, right? So then we'll be meeting on Monday with the 26th theory in Lisa and 26th paper, and on Wednesdays 27 classes, right? So we'll be meeting before this class now, because this is an extra class that you are participating. So see you there, right? So stay safe, good night and goodbye. See you.